Hello, everybody, and welcome to the Mindscape podcast. I'm your host, Sean Carroll, and today we're going to talk about space travel. One of the things that you don't necessarily appreciate when you start talking about space travel is the very different scales that we might be talking about. So we're not talking about traveling to other stars today, anyway. We're not even talking about the very down-to-earth mission of taking a gigantic rocket and launching it into space to put up human beings or satellites. What we'll be talking about is once you get there, once you're out in space, let's say you're in orbit around the Earth, how do you move around? The big problem with space travel is carrying weight, carrying mass up into space. And if you rely on conventional methods of propulsion once you're up there, that means you need an awful lot of fuel just to adjust your position in orbit. So today's guest, Natalya Bailey, is an aerospace engineer who has started a new company called Accion Systems. That's Accion. It's named after a spell in Harry Potter, not after the hypothetical small particle that could be the dark matter. What Accion Systems is doing are building ion drive engines. If you're of a certain age, like I am, you remember ion drives as being this way that you might investigate interstellar travel, because an ion drive can provide a small amount of propulsion, but for a very long time with very little fuel being wasted. So Accion Systems is building these incredibly tiny, centimeter-sized rocket engines that can be put onto little tiny satellites, like CubeSats, that you and your educational institution could build and launch into space yourselves. And then they will help you move them around from place to place. This is going to be an important part of a burgeoning ecosystem where we have a lot of new satellites in space that hopefully will not be crashing into each other and hopefully will be organizing themselves in the most efficient way. It's also a stepping stone, of course. Once you're in space at all, once you're in orbit, you're halfway to anywhere. You're halfway to Mars, you're halfway to Pluto or whatever. So this is going to be an important way that we advance the cause of traveling through the solar system in much more efficient ways. So this is a great conversation, and we did, Natalya and I are both science fiction fans ourselves, so near the end of the talk, we forget about the solar system and think more broadly about traveling through space. I do want to apologize because the audio quality on this one fades near the end. It's fine at the beginning, but the last 15 minutes are a little rougher. I tried to clean them up as much as I could. These podcasts, some of them I do at my house or in my office. Others I do remotely. I will travel to somebody else's place or at some conference or something. Some of them you got to do over the computer, right? And that's the biggest challenge. I've been investigating different software, different websites, different services to do this. Sometimes they work really well, sometimes not as well. I apologize to the listeners and to Natalya that this time didn't work as well. But I'm trying to get better at it, still new at this, and I think that I am getting better at it. So hopefully this is a temporary glitch. The content of the discussion is really, really great, so I think you're going to enjoy this. Let's go. Natalya Bailey, welcome to the Mindscape podcast.
Thanks for having me, Sean.
So there's obviously, we all know that the orbits above us, the sky above us is filled with satellites. I think maybe people don't really have a very good idea of how densely packed the space is with satellites, or how not densely packed. I mean, we're hearing about the fact that there's a lot of space debris up there, but on the other hand, space is really big, right? And you can have a lot of things up there without any of them running into each other. Could you just set the stage for us a bit? And what is the current environment up there in near Earth orbit and beyond?
Sure. So as far as the Earth orbiting satellites that are focused down here at people living on our planet, every year there are around 1,000 spacecraft launched. That number has increased from the previous kind of space industry, how we've done things for the past 50 years. It's been increasing every year for the past decade. I think we'll probably start to see numbers more like 3,000, 5,000 spacecraft launched annually. So now all of those things last anywhere from a few months on orbit all the way to 15 or 20 years on orbit. And so you can, do that math and figure out how
Yeah.
many of those are up there. But the other thing that has people in this community a bit worried is that sometimes satellites collide with one another or hit another object in space, and they themselves turn into 10,000 new pieces of debris, and that can actually have a kind of waterfall sort of effect called the Kessler syndrome, where potentially we could reach a point where there are just so many pieces of this debris in orbit that the problem kind of runs away, and we keep creating more and more debris, and low Earth orbit becomes a bit unusable for these Earth-facing applications. So we're keeping an eye on that, but like I said, the number per year is about 1,000 and growing, and it's an exciting time in the industry.
Yeah, I bet that most people, because me, didn't realize that the lifespan was only 10 or 15 years. So that means that 1,000 satellites are falling to Earth every year, right?
Yeah, that's about right.
And is that lifespan specific to near Earth orbit, low Earth orbit? I mean, how should we in our brains visualize the different places that we put these satellites?
That's a great question. So a satellite launch to about, I think it's 300 or so kilometers uh, will stay there for about a year. A satellite launched to 500 kilometers could stay there for about 20 years, and it's actually an exponential relationship with altitude, between altitude and lifetime. If you go much above 500 kilometers, and that's the distance above the Earth, you end up basically putting things there that for the all um, reasonable purposes end up becoming kind of permanent fixtures, which is not a great position to be in. So really, the UN and then NASA and various space agencies prefer that things only have about a 20 to 25-year lifetime in orbit. So that either means 500 kilometers and below, or that these objects have a way to deorbit themselves at the end of their useful lifetime.
And presumably they burn up in the atmosphere. There's not a threat that they're going to land in San Francisco and hurt people, right?
Yeah, I think I believe I read somewhere that you're more likely to be attacked by a shark and struck by lightning in the same day than you are to be hit by a piece of debris from a spacecraft.
Uh, if I take that statistic seriously, I presume that means that no one has ever been hit by a
That's
piece of
right.
debris from a spacecraft. Okay, good. I didn't realize that NASA and the space agencies actually encouraged people to launch their satellites into lower Earth orbits specifically so that they don't last. So that part of the solution to the problem of overcluttering orbit is make it temporary.
Yes, exactly. Things only become really problematic if they're up there for, you know, 5, 10, 15 years. Otherwise, they deorbit on their own.
And of course, there's the special geosynchronous orbits where you orbit once every 24 hours. You can hang out above some particular place on Earth, or at least some particular latitude. Oh, sorry,
Mhm.
longitude on Earth. But that's much further out, right?
Yeah, exactly. Much further out, much more expensive to reach. So that's more for the handful of Fortune 500 companies, and then the space agencies, and that's roughly 40,000 kilometers versus the kind of 400
Yeah.
we've been talking about.
Okay, and the environment there in terms of what satellites are up there is changing. Obviously, we have communication satellites, we
hmm
have Defense Department stuff and NASA stuff, but these days it's becoming a lot cheaper, right? To just send something into space.
Yes, exactly. So the past, I guess now maybe 15 years, you've had this fantastic combination of private money and coming into the space industry, and then Moore's law making smaller electronics still quite capable, and now we're able to package those into smaller spacecraft. You had this ever increasing demand for the internet. And so these various factors have come together, and space has, as a result, become more accessible and also more desirable for various applications, and more affordable. So smaller satellites mean that more countries can access space, more organizations. Even we're working with a high school team, and they're also hobbyists in their garage building satellites.
which I will never stop being amused by. But is this the CubeSat idea? Explain to us what a CubeSat is and why it's so fun.
Sure. A CubeSat is kind of the one industry attempt at a more standard form factor for a satellite. So, as you know or can imagine, a standardized anything basically can lead to reduced costs, and therefore more users around the world being able to leverage spacecraft. So, a CubeSat, uh, one cube, one unit, is 10 centimeters by 10 centimeters by 10 centimeters, so 1,000 centimeters cubed. And to give you a more physical sense, you could fit a softball inside
Right.
of one U. What's a little bit more popular is a 3U, so that looks a little bit more like a shoebox or a champagne bottle. And there are actually commercial companies now launching 3U CubeSats that are able to generate revenue, which is, an extremely new thing in the past decade.
And yeah, so you mentioned high schools.
Hmm.
How much does it cost if let's say I have built the CubeSat? Let's say I'm not very good at it. I just built it at home, but I trust it's going to go up there. How much would it cost me to get it on a rocket and launch into orbit?
If you are a high school, all in, you're probably spending 20 to 40,000. If you're an individual, or a commercial business, you're spending maybe 150, $200,000.
You mean they charge me more because I'm an individual, not a high school?
Yes, there are a lot of discounted launch opportunities for academic projects.
I see. Well, $100,000 is probably outside my price range for building my personal vanity satellite.
Yeah, well,
But
it keeps coming down.
yeah, exactly. That's right. And the when you say there are companies doing the launches, so they're building rockets. Obviously, we hear about NASA launches, we hear about SpaceX and Blue Origin and so forth. But how many companies are there launching things into space?
So you'll have to fact check me on these numbers, but in something like 2008, I believe there were around 80 active space companies, and then 2018 there were something like 800. And now some of those
Wow.
are not the ones actually sending things into space, but they're part of the value chain somewhere. So that gives you a sense of the growth in recent years.
Okay. Yeah. No, I really had no idea. And are they launching from their home base, or do they rent space at Cape Canaveral or something?
Yeah, there are a few launch sites around the world. The the ones I hear most about are people launching from India on their launch vehicle. Uh, in the U.S., there's the Cape, like you mentioned, um, and then on the West Coast, there's Vandenberg. There's also Wallops, and that's off the coast of Virginia, but that tends to be more of the government launches. And then our first launch was from New Zealand, so that's a new thing for the industry.
Okay. Yeah, that's cool. I mean, it makes sense to have it near the ocean, right? In case something goes terribly wrong.
Yes, exactly. Range safety, they call it. So try not to fly over children and homes and things like that.
And what are most of these satellites doing? These thousands of satellites that are going into orbit every year.
A couple main missions. Probably the most uh, prevalent one is communications. So whether that is uh, direct TV or Sirius radio, to broadband internet, to um, IoT type of services. Those all fall under communications. The other main segment is Earth observation or imaging. So using, you know, various spectral imagers to infer things about the planet for national security or climate, agriculture, asset tracking, things like that. And then, of course, you have some of the pure science missions looking at the the atmosphere, looking at icebergs melting, doing other types of earth and atmospheric science, and then some will separate out maybe military applications, but really they can be a combination or one of those three types that I already mentioned.
Right. And I presume that most of the high school ones are trying to do some science, or are they trying to do communications?
Yeah, most are doing science. One of the ones we worked with was taking pictures of Venus.
Oh, okay. That's cool. So it's not just looking at the Earth. They can look at, they can make their own little space telescope and send it into orbit.
Yeah, exactly.
All right. I did not know that. Okay. You've mentioned your own satellites, but you're not so much in the satellite business as you are in the little rocket engine business, right? So once these satellites are up there, you may be happy with where they're located or how they're orbiting, but you might also want to push them around. And that's where you come in. Is that right?
Yes, that's right. So a very typical use case for one of our systems is you launch your satellite, but maybe you had to purchase a cheaper or sooner launch, so it's not quite where you wanted to go, or you weren't put precisely where you needed to be. So you need a propulsion system to raise or lower your orbit initially. If you launch a group of satellites, you also don't want them to stay clustered together in a very tight group, so you need to phase those out along an orbit. Then, presumably your mission lasts for 5, 7, 15 years. There are all sorts of forces acting on a spacecraft when it's in orbit, especially over that long of a period of time. There's gravity and atmospheric drag and other perturbations. You may need to avoid collisions with debris, like we talked about. All sorts of reasons over the lifetime you may need to maneuver. And then at the end of your satellite's lifetime, you're responsible for making sure it deorbits responsibly and burns up in the atmosphere. So you also need propulsion for that.
Okay. So what do people usually do these days? What is the most typical kind of propulsion you would hook up to your little satellite?
Well, the status quo of the industry, frankly, has still been really large satellites, and there are existing ion engines. We build a type of ion engine. There are really large ion engines that work on a geo satellite, but those don't scale down, and so the new industry forming around smaller satellites doesn't really have a solution today. There are several people trying to scale down the traditional large technologies to fit on small satellites. Those have some kind of fundamental plasma physics limitations that we could get into. And then
Hmm.
as a kind of backup plan, it's possible to use a type of chemical propulsion, so like a smaller same technology as a rocket for launch, but a much smaller version. Those are not very fuel efficient, which is why they're not very popular. Or you could even do something like a can of compressed air and open that and use that thrust, but that's kind of the least efficient method. So those have been backup plans, but you really need something that's much more fuel efficient to close to close basically all of these business models and make these missions viable.
Right. Yeah. Let's get into this a little bit. I mean, I think the can of compressed air is a hilarious way to push your satellite around, but I think probably most people have in mind the traditional chemical propulsion where you burn some fuel and push yourself around. Compare what is an ion engine compared to that? What's the very idea of an ion engine?
Sure. So chemical rockets that most people think of when they think of rocket science or propulsion, fundamentally, you are releasing chemical energy by breaking bonds through combustion and transferring that chemical energy into kinetic energy to push the spacecraft. So you have, let's say, hydrogen and oxygen, and you combust those two fuels, fuel and oxidizer together, you end up with a very hot gas as a result, and that is forced through a nozzle and out the back of the spacecraft, and the spacecraft moves in the opposite direction. So that's chemical propulsion, and fundamentally, that's based on the conservation of momentum. Stuff out the back pushes the spacecraft forward. So electric propulsion, which is what we do, based also on conservation of momentum. Stuff out the back pushes it forward, but we use electrical energy to accelerate a charged particle out the back of the spacecraft. So electrical into kinetic rather than chemical into kinetic. and it's actually more efficient to do electrical into kinetic in terms of the unit mass. However, you need your own power source when you're doing the electrical conversion. Chemical carries the power required within the reaction, and so there is a trade-off there, and it's also a bit slower. So you send fewer particles with mass
Right.
out the back. So you need more time on orbit to accumulate to get up to the speeds that you would like to reach. But we found that most people in the industry actually have that time available and would trade it to benefit from the fuel efficiency savings.
So the very, very basic idea is you just charge up an atom, you ionize it,
Mhm.
and then you put it in a strong electric field and push it. So instead of burning some fuel, you just take some atoms that are lying around or molecules, I don't know, hopefully you'll tell me, and then you can just accelerate them as long as you have electricity and a battery or an electrical power source lying around.
Yes, that's right.
And so this, the idea of an ion engine, I remember reading, at least in the 70s, this was going to get us to interstellar space. But the technology already exists. It pre-exists. It predates your company. But you're just doing a different spin on it.
Yeah, that's right. Ion engines have been used on commercial spacecraft and on interplanetary spacecraft, but they it's near impossible to scale down this that particular technology to fit on a smaller satellite.
So what kind of technology is it that they use on the big ones?
So a conventional ion engine works by injecting a neutral gas into an ionization chamber. So they'll inject xenon or argon into a chamber, and they'll also inject a stream of high
Hmm.
energy electrons. And the job of those electrons is to find and collide with one of those neutral atoms and to kick off an electron, thereby ionizing the xenon atom. So now you have a xenon ion. And then some fraction of those xenon ions hopefully makes it to the downstream grid where there's actually two grids and there's an electric field between them. So if an ion finds its way into this electric field, it's accelerated out the back of the spacecraft, producing thrust.
Okay, I see. So there, I can already, even though I'm a theoretical physicist, not an engineer, I can detect the possibility for some inefficiencies in this initial process where you're just squirting gas into a chamber and ionizing it.
Yes. So even at the larger scales, there are several inefficiencies. You're losing ions into the walls all the time. And then as you could also imagine as you tried to scale this technology down, the first thing you do is you make that ionization chamber smaller because it has to fit on a smaller spacecraft. And what you've essentially done is reduce the amount of time, the residence time that the neutral xenon atoms and those electrons spend in that chamber. So you've reduced the likelihood that they'll collide with one another. Uh, and so you basically don't form any ions if you make the chamber small enough. So to combat that, you have to increase that likelihood again. And so you inject more high energy electrons into the chamber to improve your odds. But now you have so many high energy electrons, and many of them end up going right into the walls of the chamber. And to get back to that same ionization fraction, you actually put so many into the walls that you melt most materials known to man that could be used in this application. So it actually doesn't really close on many of the scales of these smaller satellites.
Okay, so your company is devoted Accion, right? Is that how we pronounce your company name?
Yes, Accion.
It sounds exactly like a particle physics hypothetical dark matter candidate. So, but it's spelled differently,
Right.
Accion. So you are devoted to having a better technology that can be made smaller and more portable for the ion engine idea.
Yes. So we can't get away from conservation of momentum, and we know that we want.
That would be bigger news. I would have had you on the podcast earlier.
I know. That would have been a different podcast. Yeah. And we know that we want to use electrical energy to accelerate charged particles out the back of the spacecraft. So those things hold, but how can we maybe get away from this ionization probability and needing to inject this gas and these electrons? So we looked at using instead a liquid propellant. It's called an ionic liquid, actually, and they're quite popular in the battery and electrochemical cell applications. And they're really just positive and negative ions that happen to be liquid over a wide range of temperatures. They're not in solution. There's no water or anything. It's just positive and negative ions. So we took these liquids and we said, well, can we apply this same electric field that those ion engine guys apply between their grids to accelerate their ions? But can we not only accelerate ions, can we also extract ions of one polarity out of this liquid and then accelerate them with that same potential, with that same electric field? And it turns out that if you are clever with the ways you kind of orient the geometries and design these systems, you can. And so we don't need to ionize anything on orbit. We already have positive and negative ions, so we don't need this large chamber for these collisions to occur in. We just really need that grid and this source of ions. And the reason this, my co-founder and we actually met as grad students in a lab and we didn't have entrepreneurial aspirations at the time. But the reason that there was this need for this and there was great timing was this is actually inherently happening on a very small scale. This ion emission from these liquids occurs within a region of about 20 nanometers. And so instead of taking something really large and trying to scale it down and basically tanking the efficiency, we started with this mechanism, which happens on a small scale, and now we can just parallelize it and scale it up to be able to work on satellites of all sizes.
I see. Okay, and so the main difference here is that in the chemical propulsion, the actual propellant is the same thing as the fuel, right? I mean, you burn it and then you expel it. Whereas here, you will carry around this little liquid of
Mm-hmm.
ions. It's sort of pre-ionized in some sense. I guess
Yeah,
are
sure.
the different kinds of ions
Mm-hmm.
gently hugging each other, and you can
That's
easily
right.
take
Yeah.
them apart. Yeah, and then but separately you have a source of power, which is electricity. So do you carry a battery up there, or is it solar powered typically?
So we draw power from the spacecraft. So a combination of solar energy and batteries.
Okay, and so the limit is basically how much fuel you can bring up. The limit for how much thrust you have over the lifetime of the satellite.
Yes, that's right.
And how long do you have? Is it? I mean, you're packing these into centimeters sized or tens of centimeters sized boxes. How much lifetime can you have for pushing yourself around?
Yes, well, that you just nailed the most important metric at Accion right now. We've demonstrated that the technique works now to make it actually useful to various types of missions and customers. With satellites, lifetime is the key here. So when we spun out of our lab, we were operating for 10 hours, 20 hours. Recently, we just broke 1,000 hours, and that's actually what we're ready to go to market with that. So it's on the order of thousands of hours.
Okay, that's cool. And these are, just so our audience is visualizing this, these rocket engines are really tiny things, right?
Yes. So we build a complete system with the thruster head where the ions are extracted and accelerated, but also the propellant supply system, including the tank, and then the power electronics for interfacing with the spacecraft. But um, the thruster head itself, where all of the magic occurs, is uh, we build it in thruster chips, and each chip is a square centimeter, and you can arrange any number of these chips together in different places on a spacecraft to accomplish your mission.
So it's a square centimeter and it's thinner in the third dimension, right? It's
About
less than a
two
cubic centimeter.
millimeters. Hmm.
Yeah, okay. So you basically like glue these to the walls of your engine and that's your rocket. You to the
Yes,
walls of your satellite.
right.
All right, that is a very cool idea. And has it happened yet? Are you in orbit?
Yes, well, when we were still at MIT, we launched a couple back in 2015, and just recently, Axion launched our first two at the end of last year, and now we're working on another three launches this year. So, yes,
But you're hoping to do 1,000 launches a year, I presume, or
yes, exactly.
it's a booming thing, right?
Yep.
And how much thrust are we getting out of this? Is this like a G, or it's probably a tiny little amount, I'm guessing.
Tiny little amount. Each chip produces about 12.5 to 50 micronewtons. So on the lower end of that, that's about as much as a mosquito landing on your hand.
But you keep it up for hundreds or thousands of hours, and you can actually move the satellite around, is the idea, right?
Yes, and when you're in space and not, trying to get out of a gravity well or trying to compete against atmospheric drag, the force really adds up, and we're producing enough thrust to complete most commercial missions today. So
Yeah, just to be
yeah.
super clear, because I know it's clear to me and you, but to for everyone, nothing you're doing is solving the issue of getting into orbit, right? You are not launching the spacecraft. You're gluing your little centimeter-sized tiles onto the size of it, something that's already in orbit, and nudging it from one orbit to another.
Right. We're doing in-space propulsion. So the satellite has already been launched, and then we take over from there.
And that's always going to be true, right? There's no version of this that's going to help us get into space. That's not the idea.
Um, there are universes where that's possible, where nuclear or some other, antimatter type of energy source is available to power a system like this. Right now, politically, I don't think that will be possible. But as far as the physics go, it's not impossible.
I see. So basically, because is the limitation just how strong of an electric field you can have, or is it how much fuel you can carry around?
No, actually, for launch, the current limitation is in the power supply system. So the specific power per kilogram. Most power sources that people feel comfortable launching from a country with people living in it um, that number is too low. The power per kilogram is too low. But there are there are possibilities where you could launch small things with known power sources or with some more theoretical ones in the future.
And have I heard that people are imagining like 3D printing launch systems that will get us into space? I mean, how close are we to a truly revolutionarily new relationship with getting things into orbit and manipulating them there?
Yeah, I think, I mean, even today, some of the new launch companies are 3D printing a lot of the main components, or they're innovating around having purely electric pumps, things like that. So we're getting there in terms of the components. Then there are things like operational considerations. How do you build a factory around this when your demand is quite lumpy or uncertain? And then, I mean, it's a bit of a chicken and egg problem. If they could be guaranteed, 5,000 launches per year, we could start seeing a lot of innovation on the launch side. If we could be guaranteed, $500 a kilogram to orbit, we could see more innovation on the satellite side. So fortunately, we have some really rich people that like launching stuff into space working on these problems. So I think we're heading in the right directions.
And that's not you. You're not one of those. You're the plucky little upstart.
Yeah, exactly.
And I presume that because it's in space, like everything in space, there's a lot of defense commercial or customers, I guess. I mean, there's a lot of applications for existing people. I know that just this morning I read an article where India was able to shoot down a satellite, and so they're now the fourth country that has officially been able to shoot down a satellite. And it makes you think about the future of the militarization of space.
Yes. So right now, about half of the market is government or military, and space in the 60s to 90s was a big asset for spacefaring countries. Now it's kind of flipped into a liability, and we're so dependent on it. But now it's not a a rare place that only a few people can access. So how do we protect the things we're so dependent on now up there? Um, and yeah, I think the government and military side of that will change a lot in the coming years. And there's um, a lot of things happening. If you're following the Space Force and the things happening in the Pentagon versus what's happening in the Air Force, and a lot of changes right now.
Yeah, well, I'm not really following it. I mean, so for the audience, is there specific changes that we should be looking out for, even if they're not, set in stone, but just what kinds of things are people contemplating?
Yeah, so the Air Force has traditionally been where most of the U.S.'s space activity, as far as defense, has been housed under, and um, the the point I made earlier about it becoming a place we're trying to figure out how to protect our assets in means that now the Pentagon is considering creating a separate branch of the military for space specifically in recognition of that. And so there are moves happening like that and some reorganizations as the U.S. tries to navigate our next couple decades in space.
And I can't help but think, as someone who's trained as an astronomer, one of the great things to do in space is to explore other planets. Are your engines going to be useful for that kind of thing? Either getting, once you're in orbit, getting to other planets, or once they're there, manipulating the orbits of satellites and probes that NASA might want to launch?
Yeah, absolutely. So on our roadmap is increasing the amount of thrust or power we can produce per unit area. And fortunately, the particular technology we're working on has the potential to be scaled along those lines in ways that are unlike any other electric system that's known today, whether it's flight proven or theoretical. So we have this technology has legs, and we can certainly see it being used on, um, crewed spaceflight missions or interplanetary science missions in the future, especially as we continue to improve that metric, the thrust per unit area.
Does it make sense to sort of use conventional fuel rockets to get into space and then use ion engines to guide yourself to Mars or something like that?
Yeah, until we solve that power per kilogram issue we were talking about earlier, we'll
Yeah.
continue to use chemical rockets for launch from a gravity well, which is a planet or a massive planet. So we'll continue to do that and then use more efficient means once we're in space.
I mean, how do you personally see the future in this sense?
Yeah.
There was this space race in the 60s and 70s. We went to the moon, and that was very exciting. But now the United States, correct me if I'm wrong here, we can't even get a person into space right now, right? As a country, we don't have that capability.
Yeah. So, well, right. I mean, we do send up US astronauts, but not on our own rockets. So looking looking a little bit farther ahead, I think um, there's a big question: is Mars the answer? Is the moon the answer? Is Are stations in between planets the answer? And I have my own opinion, which is that it's a bit risky to plant yourself in another gravity well once you make it off of one. So I mean that if you get off of the planet Earth, it's probably worthwhile considering building an orbiting station, maybe at around the Earth or something at a Lagrange point. Um, and I think I would change my mind a little bit more on that if there were planets that we didn't need to go terraform or that had really wonderful atmospheres and were more homey
Right.
feeling for us. We're quite frail. So I think being able to design and curate our environment a little bit more will be a more feasible next step.
I like that what you call a gravity well, the rest of us call a planet, but it's
Yeah, it doesn't have to be a planet, right?
could be a moon, I suppose. Yes, that's right. But no, so I get your point. Especially people who seem sanguine about the idea of terraforming Mars. It seems always very unrealistic to me when we're not even very good at controlling the climate of our own planet right here on Earth.
Yeah, I always come back to that too, and I don't. necessarily view it as a like, oops, we messed up this one, let's go find a different one. But I do think that, if humans are around in, 300, 400 years, it's probably because we found a way to live off of just this one planet and to diversify a little bit in terms of where we're able to support life. But I think we could probably make it easier on ourselves by not picking somewhere that's already pretty harsh right off the bat.
But you do think it did sound like before you were optimistic about just building artificial space stations and living there. Do you think that is a large scale possibility?
Yeah, and I think I see a more incremental path to doing that. You don't have to get a lot of humans to a more distant planet. You can build it in stages. Yes, I can see that line a little bit more clearly.
It does, of course. The hard part of that is that it requires taking a lot of construction materials up into space, right? If you want to make something really big, if you want to put 1 million people on a habitat that you built artificially in space, that would be quite the undertaking. But I guess you're saying, but at least you can do it bit by bit.
Yeah, and aside from, just having something to stand on Mars already, you don't really have much else. We don't know if we could use the actual materials we find there to build anything. So I don't think the situations in those terms would look that much different in the end.
Yeah. And so between you and me, I know that the government and NASA, it's not really between you and me because we're on the podcast, but
Right.
it's always looking for a bigger goal. Should we go back to the moon? Should we go back to Mars? So it sounds like you think that neither one of those obvious goals are the right ones.
Well, the objectives are a little bit different. I think there's still a lot of science to be done. You don't end up in my field working at an ion engine company without wondering about the origins of the universe and why we're
Right.
here and how planets form. So I think yes, of course, we don't understand anything yet, and so there's always reasons to visit and keep supporting those types of missions. But if we're thinking about it in the survival and longevity terms, I think there are maybe other places or other ways to consider that.
And what about, from watching science fiction TV shows, I imagine that in the future, we're going to be mining the asteroids for all of our valuable raw materials. Do you think that's feasible? And do you think ion engines are going to help us, take an asteroid and push it closer to Earth so we can mine it more easily?
Yes, I do. I do think eventually we'll be able to kind of harness the resources that are beyond just our own planet. Absolutely.
I mean, this is a crazy, unfair question, but what kind of time scale do you think that would involve?
Well, I don't I don't even necessarily think it's impossible to do today. It's more of a question of those resources and priorities. So, given how things are looking today, you could say it will never happen. Um, but I think technologically, there aren't. I don't think there are many parts of a mission like that, at least for a very near Earth object, that are actually infeasible.
Do you think I mean, how much do we know about what is in the asteroids? Is it really? I've never really understood the extent to which it would potentially be worth it in the sense that is it actually easier, more efficient, more economical to get certain materials from asteroids than it is just from here on Earth where we already are and we can breathe while we're doing it?
Yeah, so it's kind of a funny, economical argument where, I know someone that was looking into mining asteroids for things like platinum, but as soon as you start bringing back that amount of platinum to the earth and inserting it into the market, all of a sudden the value of platinum has, completely diminished. And so, how do you justify the cost of doing that? But I think if it's a matter of the energy cost of, well, it's much more expensive to go back down to earth to grab this water or to grab these other materials that we can harvest that are passing nearby, then I think there are a lot of instances where that equation works out.
Okay, that's good to know. What about, so as we're spinning science fiction scenarios here,
Hmm.
for science purposes, could we imagine using e- engines, ion engines, maybe like your own or maybe some other design, to capture objects in space, capture a comet that is passing by? I presume very informally that things that are moving by are just doing so quite quickly, and it would be an impossibly difficult task to slow them down and bring them closer. But maybe I'm wrong about that.
Um, yeah, so in poor space person form, I haven't really done the full trade through, like if you needed to launch all of the propellant from Earth and to stage it nearby until there was something you wanted to go to and attach to, and then push it closer to Earth, or do a few experiments. I haven't walked through those scenarios in much detail, but if we go back to the science fiction side of things a little bit,
Right.
I, the asteroid that passed through our solar system not too long ago, Oumuamua, that was shaped, suspiciously like a solar sail that came from, um, way outside our solar system, and this is the
Yes.
first object to pass through that has ever done that. And I absolutely think we should have done done more with that one. Very suspicious and worth studying, I think. So, yes, I hope our technology can be a part of those types of missions in the future. But I haven't walked through the full trade study.
Yeah. Okay. I think just to be fair to the audience, we should probably fill in a little bit of the details because it's amazing. I'm glad you pronounced the name of it because I can't pronounce the name of it. Oumuamua, is that it?
Yeah.
Yeah. This was this object, which is certainly from interstellar space, right? It's not something that was already in the solar system, but it for whatever reason flew through the solar system, and it was not in the shape of a little tiny ball. It was apparently more or less big and
Hmm.
flat. And I know that Avi Loeb, friend of mine, Harvard astronomy professor, suggested in a paper that, maybe one of the things it could be is a solar sail, designed by some alien civilization. Many other people poo pooed that idea, but I mean, maybe what you're saying is, look, if there's even a 1% chance, it would certainly be worth checking that out.
Yeah, exactly. And well, I think you just did a good overview of what it was, but its shape, as far as we could tell, looked very peculiar. It was shaped in such a way that, it could have captured photons from the sun or other stars to give it the force it needed to actually make it to our solar system. And then I think there was something odd about its trajectory that suggested that it had had a burst of thrust or force for some reason. And our best guess as humans is that it passed by something that heated it up and caused, gases to expand and give it a push. But I'm still hopeful that there's more there that we should have looked into. So I hope we get to the next one, and I hope to be a part of that.
I mean, don't you think, giving the aliens credit, don't you think they could have designed a craft that would have slowed down and stopped rather than just zooming by? Like spending all that effort to send an object to another star system and then only have it visit for a few weeks?
Well, I think so. We're getting into my crazy theories of various things about the
Good.
universe. So I think there's got to be other life in the sense of other, self-replicating molecules. Um, so we're not alone in that. There's other bacteria probably out there, but I'm not sure I'm convinced that any of one else that falls into that life category has solved the faster than speed of light travel problem before they were perhaps hit by a mass extinction sort of asteroid or something. But that, let's say there was other life out there, they generated a lot of knowledge, learned how to do some of these things, then were hit by some sort of impact. Part of their planet broke off and is traveling through our solar system as Oumuamua. We could probably learn a lot by studying it. So
Okay.
if I had to posit something, that's where I've landed.
No, I mean, I do think I'm very much in agreement with the philosophy that if it's such a high reward kind of gamble, then yeah, let's take it. Let's
Yeah,
at least explore that possibility. But I don't think that there is a solution to the faster than light problem. As a physicist, I think
right.
that problem is not going away. But do you think that nevertheless? And so, what if that's true? If we don't ever go faster than light, what do you think is the prospect for we human beings sending spacecraft to other stars?
Well, I mean, Alpha Centauri isn't that far away. I love the breakthrough Starshot um, ideas about using lasers to send tiny little chip-sized spacecraft past that star system and maybe take pictures and send them back. And I mean, honestly, the thing I love about that project is that every single part of it is impossible today, and it's so exciting.
Actually, yeah. Let's. I think not everyone is going to know exactly what that is. So this was a proposal. I remember Stephen Hawking was part of
Yeah.
the PR push for it, but it came from Yuri Milner and the other Breakthrough
Mhm.
Prize people.
Yeah, that's right. So there are several initiatives under the Breakthrough Prize name, and there's Breakthrough Listen, Breakthrough Starshot, and there was one other that maybe we can record my voice as knowing later. Um, but this particular one, Breakthrough Starshot, the goal was to use a I don't know gajillion watt laser to so the to accelerate tiny spacecraft with little solar sails to speed such that they could reach Alpha Centauri in I think it was 20 years, and so that they're to get them close to traveling at um, a respectable fraction of the speed of light, and that their signal could come back in time so that people in our lifetime could actually start to see this data coming back. But the laser doesn't exist. If those tiny spacecraft were to send that signal back from that far away, you would need a receiver that's the size of the distance between the sun and the Earth to capture the data. I just love, like we know what needs to be done, and none of it's possible today. But I think you have some of the smartest people in the world thinking about it, which is really exciting.
Yeah, no, that's really great, and I think that personally, since I don't think that we're going to go faster than the speed of light, but I also don't necessarily think that that should be an obstacle to going to other stars. People say, well, if we travel at point 0.1 the
Hmm.
speed of light, and then we'll all be dead if there's a human being or a set of people in the spacecraft. But number one, we could just sleep, right? We could, cryogenically suspend people. Or number two, we could come up with therapies that extend human lifespans to thousands of years. And I think that those are much, even though those are nowhere near technologically feasible now, they're much more technologically feasible than going faster than the speed of light. So we should just learn to be patient about these things.
Yeah, I'm right there with you. I think humans in our frail biological forms are the main problem there. And so instead, maybe we send some stem cells and a robot or something, and then see what happens.
I see. So that's a new idea. So you basically want to have the ingredients for a human being and send them into space rather than sending the whole human being.
Yeah, or the other way you could take it is, and kind of getting at what you said, various therapies to extend our lives. But really, I've started to buy into the idea that really our memories are really the only things that make us kind of unique. And so if we can just figure out how to read and write those, just package those into the spacecraft, and then you don't really need these animal forms anymore.
All right. I think that makes certainly. I would be surprised if the first probe that we intentionally sent to other stars had human beings on it. That does seem to be an
Yes.
inefficient way to do it. But so, what about the other way around? You hinted just before that you think it's very likely that there is other life out there in the galaxy, but maybe not other intelligent life because it destroys itself. Do you have thoughts behind these probability estimates?
Uh, yeah, so I looked at this recently. I think the odds of getting to a self-replicating molecule are very high, especially given the number of Earth-like planets in the universe. So certainly, I think that cropped up all the time. Don't ask me what all the time means. But then you have some other probabilities that need to occur depending on kind of the conditions on the planet. Like, does that life need to make it out of the oceans onto land? Do giant reptiles need to become extinct before mammals can really take over? So there, I haven't really factored those in, but the main problem I see is that to make it to that point, that probability is probably about the same probability as that whole planet getting wiped out by some sort of catastrophe. I don't know if it's self-made or from the universe.
External, yeah.
Yeah, but I definitely I while I don't think that we'll necessarily see another, craft from an alien planet because, Fermi Paradox, like why haven't we already?
Yeah.
Um, I do think there are probably signals or other signs of this life, and whether we need to travel to that planet to dig it out of the Earth, or whether it got to the point where it's able to put off some sort of electromagnetic signature or something. I'm not sure, but I believe it's out there.
So yeah, so the Fermi paradox, the idea that if any time in the past history of the galaxy, intelligent life became spacefaring, we should have noticed it a long time ago, and we haven't yet. I'll be honest. My personal favorite solutions to that are that either life is really, really hard, that it's much harder than we think because the biochemistry is not something that's fully understood yet, or intelligent life, technological life is much harder than we think. I think these are two phase transitions we don't quite understand yet. It seems that you are more inclined to think that intelligent life happens with a respectable frequency, but then somehow it gets destroyed. Is that fair?
I'm out on whether life makes it all the way to intelligent life. I guess I would say that it probably does with some lesser frequency, but yes, then the likelihood that it gets destroyed is even greater. And then the tragedy is that that knowledge is lost. So each time every form is starting over. So if we could just pass on, the atomic theory or
Right.
something, maybe then one of these civilizations could make it to light speed travel, or at least fire a little bit faster.
What is your feeling about the search for extraterrestrial intelligence as we do it these days?
Uh, well, like I said, I think it's possible there are some sort of electromagnetic signals we should be able to pick up. So I know we do that type of listening. Well, I think fairly well. And then really, I think there's probably a lot of evidence of you know life in the more bacterial sense, but we have to kind of make it to those other planets or find bits of them that have been blasted off by impacts or something passing near Earth to be able to determine that. So I kind of think it's just a matter of time.
Okay, I like the optimism there. Personally, I think that the chances that smart, technologically advanced alien civilizations are wasting their power by beaming radio waves out into space seems unlikely to me.
Mm,
Um, but again, if it's a tiny chance, it would change history if it were true. So I'm definitely in favor of looking just in case.
yeah, I will forever remain really suspicious of pulsars too. Like, what are those?
Uh,
This has got to be something that we don't understand yet.
it's always possible.
Hmm.
I wanted to end because every thing that interview with you always you mentioned that you kind of got into this game because what you really wanted to was to be an astronaut.
Yes.
Is that still an ongoing ambition?
Yeah, I'll keep applying. I've never made it past the very preliminary rejection postcard phase. And to be honest, I don't think I want to be the first person to go visit anywhere, but I still have the dream very much to go do science in space.
I mean, is it still, even with private rocket launchers sending people into space, is it still the prospect that people going into space are going to be officially astronauts, or is space tourism an option for you also?
I'm not so much of a risk taker. So I would be really into going to a space station because I needed to do an experiment that could only be done in microgravity like that. Or, maybe one of these orbiting stations will be built in my lifetime and they'll need people to go figure out how to best, design some part of it, or where to put the ion engines. And so I'll go to help with that. And I do think space tourism will become a bigger part of our lives and our discussions going forward, but I probably won't sign up.
All right. Well, I hope that they finally come to their senses and pick you for it, but not until
Yeah.
you've finished perfecting these engines, because I think that these ion engines are definitely going to be a big part of how we look at the solar system and the Earth
Yeah.
in the near future. So, Natalia Bailey, thanks so much for being on the podcast. That was a fun conversation.
Yeah. Thank you, Sean.